क्लास 5 मिनट में शुरू हो जाएगी अभी। बस वेट कर रही हूँ मैं बाकी लोगों के एंटर होने का। Oh. So, good evening, everyone. I'm Archita, and I'm a PMRF scholar at ISA Kolkata. Today, we are going through lecture 9 assignments, questions like interactive session. Now, the thing is that in the last class, someone asked me about the lapse rate, and they said that they are having difficulty in understanding the atmospheric stability and lapse rate. So, what I'll do is that in this session, I will like try to like revise the topic of atmospheric stability and lapse rate, and then we'll move towards the questions from lecture 9, week 9 assignment. Okay, so okay, this does not function. Okay, um, just a second. Okay, so I forgot that it's Adobe and I can't use my pen on this, but I will try to uh, make you understand. Okay. So, when it comes to atmospheric stability, what was said is that, uh, okay, so we'll start with atmospheric stability, and in atmosphere science there is three type of stability is being considered. One of them is, okay, so there is stable atmosphere, there is unstable atmosphere, and another that is considered is neutral, right? So in these are the three different type of atmospheric stability. Now in this, how they how they made you understand is that, let's say it's a slope, and then it's a valley, and then there is a flat surface, and let's say there is a ball here, here, and here. Now, and the condition are, this is unstable, this is stable, and this is neutral. So in unstable, what they say is that if a ball is like pushed from this cliff, either is in this direction or in this direction, it will not come back to its original position. Okay, so unstable is a situation which is non-reversible, you can say, or it means that once something happened, it uh, it cannot be reversed or changed. Or you can, or in the term of atmosphere, um, so if this is an air parcel and it is rising, okay, and this is the air parcel and this is the surrounding air. So in this, what you call as air parcel, that in an atmosphere, in a stable atmosphere, or in an atmosphere which is composed of all the gases, let's say, and has a temperature, okay, which is T air, and because of a plume somewhere, or because of a chimney somewhere, plume rises, and one particle or one air parcel of that plume has a temperature which we call as T parcel. Now in unstable, what happen is that the temperature of this parcel is higher or larger than the temperature of the surrounding air, which is the area of the air of the region. So in that case, now we know that anything which is hot, or so, high temperature meaning that the air is hot. Now hot air has low density, and anything with low density will rise. And now since it will rise, it will not come back, right? So that is what they call as unstable, because when a ball moves in either direction of the cliff, it will not come back to its original place. Okay, and so this is an example of unstable atmosphere. Now second thing is stable. So stable means that now if this ball I roll, okay, I am moving this ball either in this direction or this direction, after a while it will come back to the original place. Okay, it does not leave its region. So it it is um, it does not move or come back to its original place. So similarly, they say that if this is an atmosphere with a temperature T air, and because of a plume, a air parcel rises, which is this, having a temperature T parcel. Now if the temperature of this air parcel, that is T parcel, is low than T air, that is the temperature of parcel is lower than the temperature of air, then what happen is, it is, so low temperature means, Just a second. Okay. So low temperature means that it is a cold air compared to the surrounding. So cold air I'm saying because it has a lower temperature, right? Cold air has higher density, and anything which is dense, what it does? It sinks. So the parcel will not rise. It will stay either in that layer or either it will settle down. Uh, Next is the neutral. In neutral, there is the temperature of the parcel is equals to temperature of the air. It means that they are almost have similar temperature, and so the air parcel will generally stay in that region and will not move until further temperature change will happen. So unstable condition is actually very important for our atmosphere because what it called is dispersion. The more dispersion there is, the less pollution there will be. And stable atmosphere or neutral atmosphere in some cases leads to the inversion, or they help in the process of inversion. We'll see inversion in the further slides, but inversion causes the colder air or the pollutant to not disperse and hence lead to pollution load in the atmosphere or in the region which is near the earth. Okay, so these are the three different stability conditions that are present in the atmosphere. uh, okay, now they define it in the terms of lapse rate. Now lapse rate is nothing but if you consider this as an air parcel, and at this temperature, okay, and this is a chimney from which it has risen. Okay, so presently this parcel has a temperature T1 and it is at a height Z1. Now when it further rise or if it further sinks, depends, right? If it's an unstable atmosphere, the parcel will rise. If it's a stable atmosphere, the parcel will not stink, sink. So this temperature in both the cases, the temperature of the parcel will change. It becomes T2, and also the height that what? Yes, yes. No. See, okay. In the we cannot see air, right? But in a mathematical calculation, we need to like understand that okay, what we are considering. So for mathematical purpose, we say that air parcel is, let's say it's a cube of 1 centimeter cube area, right? And that is what they call as air parcel. That if a chimney is emitting pollution, then 1 centimeter cube of that plume is rising or sinking, that you call as air parcel. Okay. Hmm. So either it can rise or it can settle down or it can sink. So in both the cases the temperature will change, and in both the cases the height will change, right? The height changes to Z2. So lapse rate is that how much, okay, what is the change in the temperature with respect to change in the height is you known as the lapse rate. Okay, this you calculate mathematically, and okay, now three lapse rates were discussed: ELR, ALR, and sorry, DALR, SALR. Now, ELR is when you see the temperature, like there are a lot of instruments currently present, and then they measure the lapse rate depending on the change in temperature with height. So ELR is the lapse rate of environment, or you can call the surrounding. So whenever I say that this is a surrounding air, so that that lapse rate is ELR, that is already present in the atmosphere. You cannot, this is the lapse rate that is given by the instrument. Okay, for now we'll see that key. ELR is the lapse rate that the meteorological instruments or the instruments for the air atmospheric measurement give us. Okay, now DLR and SLR are theoretical lapse rates. So it means you calculate them, and you calculate them based on different assumptions. And you, so how you do is that I am considering that if this is a chimney with a stack, and the plume is, the air parcel is rising from here, right? Now first is, depending on if this air parcel is dry, it means that RH is very very low, or like almost negligible humidity, and or it's saturated, or you can say RH close to 100%, right? So in both the cases we calculate their adiabatic lapse rate. Now adiabatic is a term which is used when the temperature or heat is constant. Okay, so it means that when I'm saying that I am theoretically calculating the adiabatic lapse rate, I am saying that I am considering that if this is a surrounding air and my air parcel is in between the surrounding air, then there is no heat transfer between the uh, surrounding air and the parcel. So, or you can say that if the temperature of parcel is 10 and the temperature of surrounding air is 8, it does not matter what happened. The temperature of parcel will not uh, like it will not transmit heat to the surrounding air. Or if the roles are reversed, for example, this is 10 or this is 8, it's not like the surrounding air will transmit heat to the parcel. They will act independently of each other, and that is what adiabatic, that is what we imagine, or that is what we consider when during the calculation of adiabatic lapse rate, that there is no heat transfer. Okay, so ELR is what is given by the instrument or the of the surrounding air, and DLR and SALR is the lapse rate, which is for the which we theoretically calculate, and it is if the air parcel, that is the parcel that is emitting from the plume, has any water vapor or water content, or is completely saturated with water. So depending on the situation. Now that this situation varies, generally it says that only the dry adiabatic lapse rate is considered, because generally no one reaches that 100% level. If a air parcel reach 100% level, it convert to liquid over time. Okay, so this is there. This plot I will explain later when I'll explain the atmospheric stability. So this is same. um, okay, so what they say is that now according to theory, or according to the calculation that have been done, they say that Okay. Okay. Um, let's say this is the temperature, this is height. Now, when we study the atmospheric layer, we see that in troposphere, temperature decreases temperature decreases with height. So, ideally, this should be the trend, that here the temperature is T1, and as it reaches the height in the troposphere, the temperature changes or decreases. Okay. Now, this is the normal trend. And now, according to theory, if a air parcel is released here from a plume, then it will move in this direction. It will follow the same rule, that with height, as its height increases, okay, it becomes colder and colder, and the temperature reduces. Now, according to the theory, the for the dry adiabatic lapse rate, the temperature changes 10 degrees Celsius per kilometer. That for every kilometer rise in the height, the temperature of air parcel decreases by 10 degrees Celsius. It means that if it is 10, it means a hot air. Hot air, what it does, it rise. So it rise and it reaches this height, which is 1 kilometer. Now here the temperature is 0. Okay. Now again it reaches 1 kilometer and the temperature changes into -10 and so on. So that is dry adiabatic lapse rate. For saturated, they said that initially, uh, till it reaches the height of 1 kilometer, the the change would be same, that is 10 degrees Celsius. But as it reaches further up, the change become 6 degrees Celsius per kilometer, or even decrease depending on the saturation. So if the air parcel is highly saturated or highly enriched with water, there is a decrease in temperature change as you go up. Now, okay, and now they have given this derivation, right? Let's go through this. Okay, so what they uh, said is that, let's say, in a atmosphere, a plume is released, and this is the region where plume is released. Now, in this, the two type of force will exist, occur on it or work on it. One which try to rise it, and another which is due to gravity. Okay. Now they said that for this strip, let's say it has an area of A and a okay, it has an area A. Now the difference between the bottom and the top layer is del H. Rho is density and G is gravity. Now what they said is that uh, this okay. Now in this air parcel, if it has to be stable in the atmosphere, okay. Now the bottom and the top force should be equal to what is occurring in between this layer, right? Okay, so the air parcel rise, it this is a change in height of air parcel. So the pressure at this point, okay, and the pressure at the top. When you add it, it should be equal to the total pressure, or to the total force that is applied to this air parcel in this rectangle. So that is why Pa minus P plus dph. Dp is because with this change, okay, um, sorry, let's say this is a thin strip of air parcel. It rises. This is a point from which it rises, and this is a point till which it reaches. So this is the height it covers, del h, and an area A. Now, at this height, some pressure will be applied from the top because there are other gases in the atmosphere. And when it was there at the bottom, some pressure is still there. So, initially, let the pressure applied is P on a air parcel with area A. As it reaches a height, the pressure will be initial pressure due to gas plus the pressure change due to this height multiplied by the area. Okay, and these two are equal to the force that is applied on this particular strip, which is A rho G del H. Okay, yeah. So what they say is that if it reaches this height, now the pressure becomes the initial pressure which was there plus the change in the pressure, because as you know, right, that as you go, this is the temperature trend and this is the pressure trend as you go up the height. Just a second. um, okay, so this is how the pressure change and this is how the temperature change with the height in the atmosphere. So as the air parcel move here, because of the change in height of the air parcel, the pressure that is acting on this air parcel will also changes, right? And that is what dp by dh into del h, change in the height, and multiplied by the total area, because this is the pressure which is applied on the area. So uh, so force is equals to pressure into area, right? So the force, so ideally the total force that is on this air parcel is equals to the initial which is applying at the bottom minus the one which is applied from the top, and it is equals to the total pressure or total force that is there on this air parcel. Now what they did is that, let's say, because the air is nothing but gas, so they applied this ideal gas law, which is pv is equals to nrt, right? So if I apply on any gas which is there in the atmosphere, the law is pv is equals to nrt, which is ideal gas law. Now, so you just remember that first equation is this, because of the this is the force applied. Second, we are seeing that, okay, let's consider that the air, which is majorly composed of gas, follow this ideal gas rule. Now they changes into this. So again you can change. So they replace density. So density is nothing but mass upon volume, and mass is nothing but number of moles into molar mass or molecular weight, and this is what there is. And now nv is nothing but nv is equals to, so if I rearrange this, it becomes p divided by rt goes below p, and n by v. Yeah, yes. Number of moles. So here n by v is p by rt, right? So you know number of moles is equals to mass upon molar mass. So mass is equals to this. So molar mass or molecular weight into number of moles by volume, and number of moles by volume is P by RT. So just P by RT uh, into molecular weight. So this is the present formula of, like, density. Just did someone the ad is it okay? So the thing is that I am unable to read messages while I'm writing. So you, if you have anything, you can simply, like, tell me. एक second में देख लेती हूँ. Hmm. Hmm. So it's not see, adiabatic lapse rate is change in temperature with height, right? Adiabatic means that when the air parcel is moving, there is no heat transfer. So if I have an air parcel with temperature 10 degrees Celsius, and the surrounding air has an air parcel of 8. Okay, so in theory, what we are considering is that there is no. So, okay, I'll tell you in a very different way. So, in convection or conduction, what happen is that, let's say conduction, if I have a globe or if I have a molecule and it is heated, now it is a conducting molecule. What it does is that whatever surrounding it, okay, it try to transmit or transfer heat to that object. If I wrap a hot sphere with let's say a towel, with a towel, then, or with a piece of cloth, then that piece of cloth also become hot. That is the principle of conduction, right? Now, the principle of adiabatism or adiabatic principle is that if I have a hot sphere which of high temperature, and if I wrap it with a cloth, then there is no change in the temperature of cloth. The cloth has its own temperature which is stable, and this sphere has its own temperature. They are not transferring their temperature or heat to it to each other. That is what adiabatic means. That you are considering that if from a plume a air parcel is generated, it is not giving heat to the surrounding air, or it is not taking heat from the surrounding air. So it is an assumption, because in ideal situation that does not happen. Okay. Okay. Okay, so we were here. So now again, uh, rho is equals to P by RT mw. Now we put it in the equation 1. So equation 1 is here. So what they say is that they make this entire thing as, I think, dp by p. No. So they put this entire term as dp into dh. Then there is area p upon rt into molecular weight into g into again dh. So del h or dh you can uh, okay, just a second. So they simplify this equation into okay. So ideally the equation was P minus P dh, sorry, dP by dh into del h is equals to A del h rho g. Now now you multiply this here, so it becomes P del H minus P, again this del H is there, dP by dH A is equals to A. Now, so they remove A with A, so PDH. So 1 minus dP is equals to mm, and this becomes 1 minus del P is equals to del H rho G, and if you change it, it becomes 1 minus 150. Just a second. Sorry. Okay, P slight errors. एक second. Okay. So the equation is PA minus P now you take A common. This is no, A will be cancelled, but A will be cancelled when I take this as P minus, so this become PDH plus dP by dH. The thing is that if I P1, I'm not understanding how P comes in the denominator. That A will be cancelled, but this, this is del H. Now this become PA dH minus, so Okay, okay, okay. Yeah, correct, correct. I forgot one thing. So this become A rho G del H. Now it becomes minus dp del H A upon dH is equals to A rho G del H, del H, del H, A and A. So it is minus dp upon dH is equals to rho G. Now the value of rho is here, which is P. So minus dp by dH is equals to P divided by RT into molecular mass into molecular weight into G, right? And this equation becomes dp by P. You can put this negative here also it's same. So they have put it in this direction, minus mw into G divided by RT, RT, and this del H goes there. So del H. So this is the equation that comes. So what I did is, okay, so the equation was the initial pressure minus pressure at as the parcel rise, and first I multiplies this dH with this P. So P dH plus del P del H. Now I multiplied because again this PA is there, so I have to make this entire equation. So PA dH minus, now this P dH should be multiplied with this A there, and this dPH del A should be multiplied with the here, divide by dH, and they cancel. Now left is minus dp del H A divided by dH is equals to A rho G del H. So del H cancel, A and A cancel. What we left is minus dp by dH is equals to rho G, and you saw put the rho value which we calculated here using the gas law, and we come up with this equation. Okay, now we reach till here. Now they say that we know that adiabatic flow rate, in adiabatic process heat flow is zero. So they put conservation of energy and they equate it. So I have no clue how they write this equation, but uh, the mechanical. So this is the decrease in internal energy, and this is the work performed by the air. So they have written that work performed, that if a air parcel will rise a height h, and with rise the density is changing and the pressure is changing. So the uh, so according to me they have written this equation based on uh, they have to equate the work performed by air with the internal energy of parcel. And how they did it is that the work performed by the air depends on the pressure, depends on its density, and depends on the change in height, right? And they equate it with decrease in the internal energy of a of the air parcel. It's not so with change in temperature with height, which is basically nothing but lapse rate, that how the lapse rate multiplied with the heat capacity, right? Hmm. Now why we have taken heat capacity, it's the because based on the heat capacity we can say if the air parcel will lose the heat or will not, like, lose it. So uh, heat capacity means that how much heat a parcel can retain or hold, right? So based on that, how the temperature is changing and how much it can hold, we determine the internal energy of the air parcel, which should be equal to the work performed by the air. That is, how much the air. So this is for the surrounding air. For surrounding air, we have factors like height, density, and the pressure. So this equation they have equate this, and now they put, what they do is they put the they will put the value of pressure, I think. Yeah. So they put the value of P by rho. Okay, so uh, they rearrange it to this equation. dP is equals to, so dP by P is equals to minus, they rearrange it. So T is equals to minus mw g upon r dP, and this is P. Okay, sorry, P by dP होगा, लेकिन they have put this thing as density. Hmm. So they have written this as density, which I don't know how they have come up with this equation, because change in gravity with pressure is not density. Okay, so I will check on to this, but then they differentiated it with respect to height, and they put the value. So they differentiated this equation. I will check how they put this row here, and based on this, from equation 3 and 4. Okay. Mm-hmm. Huh. It should be. Uh, See, they have. Okay, yeah. See, yeah. So first, this is what they are using. So first, when they differentiate, they kept P as constant. They differentiated rho with respect to H, and in other they kept the density constant and differentiated pressure with respect to height. Yes. So then they come up with this. So I personally don't think that you need to remember the derivation, but the important thing is what comes here, which is the calculation part. So um the thing is that like there can be a question where they ask about the uh, to find the DLR of a parcel which have a molecular weight of this, or rising at a height of this, or change in temperature. So um, you can so you need to remember this formula, which is change in temperature with height is equals to minus g into molecular weight divided by r plus heat capacity into the mw dash. So I think this is the change in molecular weight of gas or the surrounding air. And here what they did is, it's important I think for numericals, that if you cannot know the heat capacity of every gas, or the change, or the final molecular weight. So they have come up with the term that the it is equal to 5 by 2 of the gas constant for the diatomic gases. That, let's say, in an atmosphere you only consider all the gases which have two atoms, which is O2, H2, N2, whatever. And in those gases, the the heat capacity multiplied by the final or molecular weight is equals to 5 by 2 r. So this line I think is important. If any question on the adiabatic rate will come, then you can simply do this. um, you can simply have the gravity value, you have the molecular weight which should be given, okay, of a particular gas, or the air parcel, temperature is there, height is there, and gas constant value is, all you need is cv into mw dash, which is 5 by 2 of r. Okay, and then you can find this 9.8 degrees celsius per kilometer, or 10 degrees celsius change per kilometer. uh, yes. हाँ बोलो. Kavya, right? Okay. um, Now similarly, what they have done is, they have done it for the wet adiabatic lapse rate. Now they could not come up with any with any equation for the same, so they have just written this formula. I don't think you will ever have to use it, because as sir also mentioned, that wet adiabatic lapse rate generally people don't use, because in that case you need lot more parameter compared to dry adiabatic lapse rate. For example, here you need the dry air constant as well as the saturated air constant, gas constant. Then you need to know specific capacity at a particular, at a constant pressure. Then you need to know these two, which is, you also need to know the dry adiabatic lapse rate of the molecule, then the latent heat of vaporization, and this parameter, which is the mixing ratio of a parcel. So mixing ratio again depends on the density of the air parcel. So I don't think anyone will ask you to explain or use this. So you can just stick to the dry adiabatic lapse rate. Know that what is its formula, how you calculate if someone asks uh, for the uh, for the value of temperature or height of whatever for the dry adiabatic lapse rate. Now here they say that the initial temperature is 10, and initially there is no moisture. Okay, now as the air parcel, so for the first 1 kilometer, the air parcel act as a dry air parcel and will follow the dry adiabatic lapse rate. As the air parcel rise above, the temperature is changing, and the parcel is getting more and more moisture. Now if the parcel start getting moisture, then after the first 1 kilometer, the change in temperature decrease to 6 degrees celsius per kilometer. Okay, because the answer also is given that as the temperature is decreasing for a parcel, or the parcel is cooling, the heat is releasing from the particle or the air parcel via condensation, and this condensation leads to the warming of the parcel, or warming of the, okay, So this heat is more than the cooling effect because of the rise in because of the decrease in temperature, right? And hence the overall temperature will be reduced. So ideally, so what they want to say is that ideally, as the parcel is moving from here to here to here, okay. So this is the dry adiabatic lapse rate. Initially, there is no moisture content. Now, from 10, it reaches 0 degrees Celsius. At this height, it start because of the what we are considering is that it is losing heat, and it is losing heat, so there is condensation around it, and the this condensation, or the effect of this condensation, is more than the effect of cooling. Okay, so cooling, because we are saying that as it reach here, another 1 kilometer, it two forces will act. One is adiabatic force, which help in the no heat transfer of the gas, okay, of the air parcel, sorry. So the air parcel is saying, okay, I am adiabatic, I will not transfer heat. But because it's already losing heat and it is moist, or what happen is that surrounding the air parcel, the air particle, okay, or the surrounding air around the plume particle, or the air parcel, will start getting condensed, and this condensation is more than the adiabatic cooling. So the temperature here is high, the temperature because of cooling is low, and the overall sum of the temperature leads to reduction. That is why instead of 10 degrees Celsius, the rate is only 6 degrees Celsius. So the high, more the moisture in the particle or the air parcel, more condensation. So you can say that condensation temperature minus adiabatic temperature will determine that uh, the how much temperature will change. If the condensation temperature is very high, then this will become even lower, -4 or even -3, like that. That is what adiabatic lapse rate is. Mm, it is same. So this is what they say, that if the pressure is high and is 100 MB, okay, this is if this is 1000 MB, and the temperature is high, which is 880, then here the uh, change in the wet adiabatic or saturated adiabatic lapse rate would be even lower, which is 6.67, which is 4.67, which is here, sorry, this is 288. So, and as the temperature is lower, which is around 240 C, the temperature is 9. The change in temperature with height is 9. As the temperature increases, more condensation, and hence there will be more uh, wet adiabatic lapse rate. Okay, now comes the stability part. So will see stability in terms of, let's say, this is height, this is the temperature. Okay, in troposphere, the ideal scenario of height is this, of temperature is this, that as the height changes from Z1 to Z2, the temperature changes from T1 to T2, and it is decreasing. Okay, now we considered this, which is the actual trend of temperature, as ELR, which is the environmental lapse rate. That if ideally in a ideal environment or in an ideal atmosphere, what should happen is that the bottomest layer of air should be hot, the top is colder, then even colder likewise. Okay, this is the ideal way the temperature profile should behave. Now comes the hypothetical lapse rate, which is the DLR and ALR. Now, if the condition we say that the atmosphere is stable, okay. Now, what I said in the first is stability, right? Huh. Okay. Let's say if I say that the atmosphere is stable, we have seen that in stable atmosphere, T parcel is less than the T air, or you can say that the dry adiabatic lapse rate or saturated adiabatic lapse rate should be low than the environmental lapse rate. Okay, this should be the ideal scenario for atmospheric stability. Now, if on this line, if I draw a line here, I'll do it here, and if I draw a line here, okay. So on this side, what is happening is that the temperature is changing slowly, slow temperature change, then ELR, right? It means this side is, if a parcel is on this side, it will be hotter compared to if the parcel is on this line. Yes or no? Understand? Someone understands? Or shall I repeat? You did not understand. Okay. Okay. So this is, you understand this much, right? That this line is the ideal scenario of how the temperature should behave, right? Okay. Now, uh, let's say I consider this temperature as mm, is T2. Okay. And let's say now I have a plume जिसका एयर पार्सल जो है इट्स बिहेविंग लाइक दिस, उसकी टेम्परेचर प्रोफाइल है ये, विच इज, एंड इफ आई एट अ हाइट Z2, this T-2 is this. Now you tell me that which temperature is high, T2 dash or T2? If you consider this is 0, 10, 20, 40, 50, which temperature is high, T2 dash or T2? Huh. T2 is high. No, T2 is low. T2 is 10 degrees Celsius. T2 dash is 35 degrees Celsius, let's say. Right? You, so this x-axis is temperature, right? It's changing from 0 to 50, 100, 200, whatever the temperature is, right? And y-axis is the height of the atmosphere, right? Okay. Now I am saying that in troposphere, what happened, that with increase in height, that is Z2 is, let's say it's 100 and Z1 is 10 meter. Okay, so with increasing height the temperature decrease. Okay, this is the ideal scenario. Now what I'm saying is that let's say a air parcel is there. Okay, and now you consider this air parcel as independent. Let's say it's a balloon. Okay, simply consider it's a balloon. Okay, and it's rising, and this balloon can change temperature, लेकिन सिर्फ अपना टेम्परेचर चेंज कर सकता है. सो यहाँ पे इस बलून का टेम्परेचर था 40, एंड एज इट मूव विद हाइट इसका टेम्परेचर हो गया 35। टेम्परेचर तो डिक्रीज ही होगा हाइट के साथ, लेकिन आइडियली एटमॉस्फेयर में मान लो जो ये एयर है ये सराउंडिंग एयर है, एंड सराउंडिंग एयर का जो टेम्परेचर है वो क्या है, वो है लेट्स से 10 डिग्री सेल्सियस। You understand? This is the temperature of the air parcel, independent air parcel, जिसको आप बलून समझ लो कि एक बलून है जो सराउंडिंग के साथ तो टेम्परेचर चेंज नहीं, मतलब हीट ट्रांसफर नहीं करेगा, लेकिन अपने आप में अपना टेम्परेचर चेंज करता जाएगा हाइट के साथ। तो अगर ऐसे ऐसे सिनेरियो है और ये टी पार्सल है मेरा, तो इस केस में क्या है, T2 डैश इज मोर देन T2, राइट? और ये कंडीशन कौन सी है, स्टेबल की अनस्टेबल? हाँ, अनस्टेबल है। क्यों? क्योंकि इस केस में हम कंडीशन हमेशा पार्सल के हिसाब से डिफाइन करते हैं। इस केस में पार्सल का जो टेम्परेचर है वो सराउंडिंग एयर के टेम्परेचर से ज्यादा है, तो अनस्टेबल कंडीशन है। अब एक और सिनेरियो ले लेते हैं कि ये है और ये हाइट है सेम, ये ELR है, यानी कि सराउंडिंग एयर का लैप्स रेट है, ये टेम्परेचर है वेरिंग फ्रॉम 0, 10, 20, 30, 40 whatever। अब जो मेरा एयर पार्सल है वो क्या कर रहा है, वो यहाँ है। इसका मतलब है कि ये मेरा एयर पार्सल है। तो इस केस में क्या हो रहा है कि अगर मैं यहाँ पे T2 कंसिडर करती हूँ और इसका यहाँ पे T2 डैश कंसिडर करती हूँ, अब इसका टेम्परेचर यहाँ पे कितना है, 0, और यहाँ पे कितना है, 15, राइट? मतलब मैं ये कंसिडर कर रही हूँ कि जो मेरा एयर पार्सल है, ठीक है, अगेन बलून है, ओके, जिसका टेम्परेचर है लेट्स से 10 डिग्री सेल्सियस, और मेरी सराउंडिंग एयर है जिसका टेम्परेचर है 8 डिग्री से 8 या 5 डिग्री सेल्सियस लगा लो। आइडियली में दोनों कोल्ड है, राइट? अगर देखा जाए तो 10 भी इतना ज्यादा टेम्परेचर नहीं होता और 5 भी इतना ज्यादा टेम्परेचर नहीं होता, लेकिन अगर आप कंपेयर करो तो 10 क्या है, ओके ओके, इट्स द अदर वे, जस्ट अ सेकेंड, समवन मैसेज, राइट? Okay, yes, we can discuss at the end of this session. First, we'll do this lapse rate thing. So, I just wrote something ulta, so I'll just a second. Okay, so what I'm saying is that this air parcel has a temperature 5 degrees Celsius, or let's say not 5, it's also hot, so it is 45, and the surrounding air has a temperature of 35. Now both the uh, again I why I do this, this is 25, sorry. Okay, so ideally both of them are hot if you see the temperature, but the thing is that air parcel is less hotter compared to the surrounding air, so we'll consider it as cold for now. It is colder compared to the surrounding air, and let's say initially this air parcel started at 25 and it reaches 0, and this surrounding air has a temperature of 35 and it reaches 15 at a height of 100 meter. So at 100 meter जो हमारा पार्सल है, जो हमारा बलून है, उसका जो टेम्परेचर है वो हो गया 0, एंड जो हमारी सराउंडिंग एयर है विच इज डिफाइंड बाय ELR, उसका टेम्परेचर कितना है, उसका टेम्परेचर हो गया 15। सो डिक्रीज दोनों का टेम्परेचर हुआ है, लेकिन पार्सल का टेम्परेचर ज्यादा डिक्रीज हुआ है कंपेयर टू द सराउंडिंग एयर। ओके, रेट इज सिमिलर बट टेम्परेचर डिफरेंस इज लार्जर। सो हम क्या बोलेंगे कि दिस पार्सल इज कोल्डर एंड इट विल सिंक, ये बोल रहे थे ना हम। सो हम वही इसी बेस पे सिनेरियो बनाया इन्होंने कि अगर मेरा एडियाबैटिक लैप्स रेट है ये, तो इसका इस साइड जो भी होगा वो होगा कोल्ड, और इसके इस साइड जो भी होगा वो होगा हॉट। ठीक है, यानी कि जो टेम्परेचर मेरे एयर पार्सल का, ठीक है, ये आइडियल टेम्परेचर है कि अगर सराउंडिंग एयर का टेम्परेचर ये है, तो अगर मेरा एयर पार्सल का टेम्परेचर कहीं भी इधर लाई करेगा, इस रीजन में लाई करेगा, तो मैं क्या बोलूंगी कि वो एयर पार्सल क्या है, कोल्ड है, और वो एटमॉस्फेयर क्या है, स्टेबल है। ठीक है, अगर अगर मेरा कोई भी एयर पार्सल इधर लाई करेगा, विच इज ऑन दिस साइड, विच इज ऑन द हॉटर साइड ऑफ द ELR, मैं बोलूंगी कि वो मेरा पार्सल क्या है, वो है हॉट, वो क्या करेगा, राइज करेगा, और कंडीशन होगी अनस्टेबल। सो हमें ये चीज ध्यान में रखनी है कि ELR के एक साइड पार्सल कंसीडर होंगे कोल्ड और एक साइड होंगे हॉट। अब बेस्ड ऑन दिस हम स्टेबिलिटी डिफाइन करेंगे कि एटमॉस्फेयर कैसा स्टेबल है, अनस्टेबल है, क्या है। ठीक है, तो सेम हमने वही बना दिया, एक प्लॉट बना दिया, ये ELR है मेरी, ये स्ट्रेट लाइन है बाय द वे, वो नहीं बनी बट ठीक है। नाउ स्टेबल कंडीशन का मतलब है कोल्ड, कोल्ड का मतलब है कि आपकी जो लैप्स रेट है वो किस साइड आनी चाहिए, इस साइड की इस साइड, इस साइड, राइट, है ना, क्योंकि ये हमारी कोल्ड साइड है। तो जो मेरे लैप्स रेट आएंगे वो किस साइड आएंगे, वो इस साइड आएंगे, विच इज SALR एंड DALR। ओके, और जस्ट 1 सेकेंड, सॉरी। नाउ मैंने इसको ऊपर क्यों लिखा है और नीचे क्यों लिखा है, बिकॉज फॉर SALR द रेट इज रिलेटिवली लो कंपेयर टू DLR, राइट। इसका 6 डिग्री सेल्सियस है रेट ऑफ चेंज ऑफ टेम्परेचर, और इसका 10 डिग्री सेल्सियस है। तो ड्राई एडियाबैटिक लैप्स रेट वाला एयर पार्सल जल्दी ठंडा होगा, राइट, और सैचुरेटेड वाला कम होगा। तो इस केस में जो सबसे ज्यादा टेम्परेचर होगा वो ELR का होगा, और सबसे उसके बाद होगा सैचुरेटेड वाले का, और उसके बाद होगा ड्राई एडियाबैटिक लैप्स रेट का। और ये कंडीशन है हमारी एब्सोल्यूट स्टेबिलिटी की, जिसमें सो वी कैन से एन एटमॉस्फेयर इज एब्सोल्युटली स्टेबल अगर ELR यानी कि जो सराउंडिंग लैप्स रेट है, सराउंडिंग एयर का लैप्स रेट है, वो सबसे ज्यादा हो, और जो बाकी एयर पार्सल है, जो प्लूम से हमें हवा आ रही है, उसका जो टेम्परेचर है वो इससे कम हो। ठीक है, और क्योंकि सैचुरेटेड का जो सैचुरेटेड है एडियाबैटिक लैप्स रेट, उसका रेट ऑफ टेम्परेचर डिक्रीज इज लोअर देन ड्राई एडियाबैटिक लैप्स रेट, इसीलिए सबसे लो में ड्राई आया है। ठीक है, तो ये हमारी कंडीशन हो गई। इन्होंने उल्टा लिखा है, उल्टा मतलब इट्स सेम, बट इन्होंने क्या लिखा है कि दिस विल बी कोल्डर, दिस विल बी हॉटर कंपेयर टू इट, एंड दिस विल बी द हॉटेस्ट, क्योंकि इसका टेम्परेचर सबसे कम है, ये कोल्डेस्ट पार्टिकल है, ये उससे हॉट पार्टिकल एयर पार्सल है, और ये सराउंडिंग एयर है। सो DLR, SLR एंड ELR। ओके, सो मैंने जो लिखा है वो उसके हॉटनेस के टर्म में लिखा है, इन्होंने उसके कूल होने के टर्म में लिखा है कि कौन सा पार्सल कितना कूल है। नेक्स्ट इज इंस्टेबिलिटी, तो कंडीशन ऑलमोस्ट लाइक परफेक्टली इनवर्स हो जाएंगी। हम क्या करेंगे कि हम ड्रॉ करेंगे, सेम ELR ड्रॉ कर दिया। अब अब वो कौन, फॉर अनस्टेबल इट शुड कम इन दिस डायरेक्शन, yes, so this will be uh, the dry and saturated adiabatic lapse rate. Now again the rate of change of dry is more, so this will be DLR and this will be SLR, right? Hmm. करेक्ट, क्योंकि अगेन सेम। सो जब यहाँ से यहाँ पे एयर पार्सल जाएगा तो वो 6 डिग्री सेल्सियस होगा, लेकिन जब यहाँ से यहाँ जाएगा तो वो 10 डिग्री सेल्सियस के चेंज पे जाएगा, राइट। सो इस केस में ईएलआर सबसे ठंडा पार्सल होगा, उससे कम ठंडा होगा डीएलआर एयर पार्सल, और उस सबसे ज्यादा गर्म पार्सल कौन सा होगा, सैचुरेटेड एयर का। एंड दिस कंडीशन इज कॉल्ड एज इंस्टेबिलिटी और एब्सोल्यूट एटमॉस्फेरिक इंस्टेबिलिटी। सो ये दो तो हो गई मेजर कंडीशन की, एक में कोल्ड की साइड है और एक में सब कुछ हॉट की साइड है। ओके, नाउ कम्स दी conditional stability. Now, what they meant by conditional stability is that if the particle is saturated, okay, it means if it has water vapor along with the plume air pollution, then it will be warm. If it is dry, it will be on the cool side. Okay. Yes. So it differed because I said, right, that if this is ELR, then this region is colder region, this region is hot. You understand this part? Huh? I could not hear you. Hello? Okay. So you know that this region would be hotter. Now I am saying what happened when the air parcel is hot. What is the condition of hot air parcel? The unstable condition, right? Right. Okay. Now I am saying that if I have a air parcel and okay, and this is, now I have two air parcel. One is saturated, another one is dry. So in all the cases we have two air parcel. One is dry, one is saturated. So अब मैंने दो air parcel बना दी, 1 and 2. Now the temperature is changing. And this is T2 double dash. Now tell me what is the temperature of T. The temperature of T2 double dash is higher than T2 dash and is higher than T2. Yes or no? Okay. Now this T2 dash, it means that if a air parcel has risen, okay, its temperature did not decrease a lot. Okay, so let's say the initial temperature of all of them is 8. You can, and the surrounding air has a temperature of 5, because surrounding air is measured, already measured. You cannot change this. This is the initial temperature of these two air parcel. Now for T2, the change is that from 8 it goes to 7, or let's say I'll take it like this. So this is 10, this is 10, this is 5. You consider 5 only. Now as it reaches height, for T2 it goes 4, and for this it goes 0. Now the difference is what? Here the temperature decreases with the rate of 6 degrees Celsius, and here the temperature decreases with the rate of 10 degrees Celsius, right? Okay, and this temperature is same. It decreases at its own pace की 5 से धीरे धीरे करके -1 चला गया, like that. So this, what is this scenario is what? It's for the saturated condition, that in a saturated adiabatic lapse rate, the decrease in temperature is lower compared to the dry condition. Yes or no? Right. So the T2 dash should belong to the saturated adiabatic lapse rate. and T2 dash, double dash belong to this, and T2 dash belong to dry adiabatic lapse rate. Okay. Okay. Now, and if, yeah, yeah, so the 10 minus 6 is 4, right? Huh. So the final temperature is 4, 0, minus 1, right? So 4 degrees Celsius is hotter compared to 0 compared to minus 1, right? Okay. Okay. So I said that in saturated adiabatic lapse rate, it means that if a balloon, uh, like a air parcel which is in the form of balloon, okay, this is balloon and it has air. Now, if it, along with air, it has moisture to it, okay, it has moisture also, then you call this parcel as saturated air parcel, right? Hello. Yeah. So as this saturated air parcel will rise, we have seen in the previous slide that for the saturated air parcel, the change in temperature with height is minus 6. It means that there is 6-degree decrease with kilometer, right? And similarly, there is a balloon which is dry. It means no moisture. Then for this, the temperature decrease would be 10 degrees Celsius. Now, if in the same case, it says that if here this, if here they started with the same place, let's say, okay, not same place, let's say they started differently, and here uh, the initial temperature is same for both, but the only difference is that one has moisture, another has no moisture. So with height, their temperature change would be different, right? It means that one loses its heat more faster compared to another, right? So as one will lose heat more fast, which is the dry adiabatic, uh, lose more heat because it is, the temperature is changing with 10, with the rate of 10 degree compared to saturated where the decrease is only 6. So that is why I draw that the lowest change is in the SALR than DLR. Okay. And this condition, and irrespective of, even if it's T2 dash or T2 double dash, both of them are hotter compared to this, right? Anything is considered more hot or high temperature compared to minus 1, right? 0 is, or 4 or 10 or 20, whatever, and they are on the hot side. That is why this condition is called as unstability or instability condition. Okay. Yeah, so they move from colder to the hotter section. Yeah, because ELR is the environmental lapse rate. So in environment, we are considering that with high, the temperature is changing, and this is what you are measuring. So ELR is measured, and this is what you calculate different uh, based on the different value you get. Depend on ki you are hypothetically thinking that okay, if a plume is released and it has a temperature of 10 degrees Celsius, then and it reaches a height of let's say 100 meter, what would be the change in temperature? Now what would be the change in temperature if that plume also has some water to it? So you are hypothetically calculating for different scenarios. Okay. Now comes the conditional stability part. So in conditional stability, you are saying that if a particle is saturated, okay, then it will lose heat. It will be hotter, okay, because we know that the change in heat or the change in temperature for saturated particle is lower compared to so you can consider it as this. um, Here what you are saying is that um, so let's say my ELR changes from 40 to 30. My SLR, that means that a saturated parcel also started at 40, and because it is losing heat less rapidly compared to the normal air, it reaches here at about, let's say, 36 at this height. The temperature is 36. Now, compared to that, my dry adiabatic lapse rate is 40 and it is losing heat with the speed of 10. Okay, it's losing heat fast and it reaches here at 20. So, what you have is that the dry adiabatic lapse rate, it means that if a air parcel is dry, okay, it will it will be colder, okay, and it will sink compared to ELR. It all depends on the temperature of ELR. And if a parcel is saturated, and because a saturated parcel heat lose heat less rapidly compared to the DLR, it will rise. And that is why there are two different places, one at hot and another one at a cold region. See, so this is the condition, this is the conditional stability. That, so this is unstable, right? This region is unstable. So if a particle is has moisture, then it will be unstable, and if a particle has this is does not have moisture, it will be a stable atmosphere. That is why it's a conditional stability. It depends on the moisture level of the particle. Now comes the wet neutral and dry neutral. So wet neutral means that the as the name suggests, neutral. So wet neutral means that the saturated parcel has same temperature as the surrounding air, and dry neutral means that the dry parcel has the same temperature or same rate of change of temperature as the surrounding. So this is what happening, that SLR and ELR are same, and it's a stability condition. So DLR is at the stable side or the colder side. So if a particle is dry, then it will lose heat and it will be on this side, okay. So it's always like that, that a dry, take it as this, that dry parcel lose heat rapidly. So always or most of the time it will be on the colder side, okay. SLR or the saturated parcel is uh, more stable or more you can say lose heat slowly, okay, because it has a 10 degrees Celsius rate and this has a minimum 6 degrees Celsius rate of heat losing. So it will be mostly on the hot side, and this is what happens. So here, if a parcel is saturated, then the rate of change of temperature of the air parcel, it will be same to the surrounding air. And if the parcel is dry, it will be in the colder side and it will sink because the heat loss is more rapid in the dry parcel. You change it here, the SLR is on the hotter side, right? So here, if a air parcel is dry, does not have any moisture, and it is changing the temperature similarly, as similar to the environment, then they are same. And because the rate of change of SLR is slow, it will be on the hotter side. So for the neutral, this is the case, that wet neutral SLR is equals to ELR, and the DLR will be on the colder side. Similarly, for dry neutral, the DLR and ELR are equal, and so the saturated parcel or the SALR will be on the hotter side. You understood this, or shall I repeat this? Okay. Then comes the extreme stability or condition. So extreme stability means when we consider inversion. Okay. Inversion means that ideally this should be the ELR, that the temperature is decreasing with height, but what happen is that ELR is this, which is a very odd case. It means that the temperature here T2 is more than T1, and when this is the case, it is an inversion case. And inversion is nothing but when one low temperature air sandwich between the high temperature air, something like that. So when a sandwich sort of atmosphere form, this is the inversion. And in both the cases, so in this, wherever the uh, irrespective of where the DLR and SLR are, the parcel will not move. Okay, so we say na that if it's cold it will sink, and if it is hot it will rise. But in inversion it will stay there. Okay, it will stay in between these layers. There is no upward or downward movement, and that is what you call as extreme condition of, or extreme stability, when the parcel, because now everything is cold, right? This region become cold, right? uh, this entire region of this side of ELR, which becomes colder. So whatever the temperature of the plume or the air parcel it will be, it will always be lower than the surrounding air, because surrounding air is hot. It's always hot, and in that case, the plume will not move and it will make a stable layer. Um, okay. So shall I continue, or shall I continue this in next class? Okay. Okay, so in next class I'll discuss this super and subadiabatic thing, and I will discuss this part, which is the plume type, that how the plume time changes with the this one plume type with the stability. Okay, so if there is nothing, then if you want to ask anything you can ask, otherwise for today we are done. We'll continue it in next class. Some one of you has to ask something, right? Which one was? Okay, if no one has to ask anything, that's fine. Hmm. Yes, yeah, I will discuss inversion also in next class. Okay, yeah, yeah. Bolo, yeah, I can hear you. Oh, sorry. Okay, Yeah. Yeah, in the case of inversion, yes. Because see, if the temperature of, yeah, yeah, because the rate is it's always the rate of change of temperature. So SALR has a low rate, right? So even if it's changing, it should always remember this, that SALR should always be hotter compared to DLR, because their rate of change of temperature is different. One is 10, another is 6. Yeah, yeah, yeah. Yeah. Okay. Thank you. So we'll continue this lapse rate only in the next week class. Okay. Thank you, everyone. Thank you.